Okay. Okay, let's get started. Um, so last class we talked about how to overwrite the save the EVP. So we do not have to overwrite the return address, but we can still control the EIP, let the EIP jump to our share code. So if we can only overwrite the save the EVP, we can basically create a fake stack frame for the upper layer function. So eventually the upper layer function will return to our shell code. So today we will talk about existing approaches to defeat so far what we learned. So most of the approaches have been deployed in production systems. So your phone, your laptop, your tablet, they already have those defenses. So before we talk about that, let's talk a little bit about the Crack Me 4, the hard version. So how many of you solved it? Okay, so you solved it by jumping into print flag, or you solved it by setting up the stack like that? Okay, yeah. So this one, like I said, is hackable, but the first time I designed this, I didn't want it to be like this. However, because the way I compile it, the function we compile generated was a little bit different, the main function. That's why it's a little bit more difficult. So let's take a look. So I hope especially for people who solve this gives you more confidence. You just need to understand the code line by line, okay? As long as you understand that, you will be able to solve it. So the main function here has a buffer, it looks like 8 bytes, compare two command line arguments, then do a string copy from your second command line argument to the buffer. So the second command line argument can be arbitrarily long here. You can fit anything there. That's why there is a buffer overflow to overflow the buffer. And because of that, you can imagine you will overflow the stack of the main function. So one way to do that, the goal is to overflow the stack of the function and set up the parameters for print secret. So eventually you go to print secret and compare those 3 arguments. Then you can print the flag. Well, there is an easier way is you directly jump to print the flag, right? Guys, be quiet, please. What are you talking about? Okay, so you can directly jump to the flag, but that's not what we want to do here. Well, for the homework, as long as you get flag, it counts. But here I want to show you why this one is a little bit difficult than the 32-bit version, or the long H hard version. The problem is, for example, for the normal version, this is what the beginning of the function look like. We have the push EBP, we have the move ESP to EBP, then we have a subtract something to the ESP. So this is the standard prologue we have been familiar with. I'm saying a lot of functions, they start with those instructions. However, the problem is, if you check the hard version, you can see it's different. It doesn't begin with those instructions. It doesn't end with other instructions. So you probably get confused here. Why is that? The reason we have this is because the main function is trying to align its own stack frame at a boundary, like 8 bytes or 18 bytes or 16 bytes of boundary. Try to align that. That's the purpose. And by default, when you compile with GCC, the GCC will compile a function like that. We can disable that. That's for the easier version. I disable it. So here we don't care where the stack is, but this one we do care. So what happens here is, if you fully understand what's going on here, then it will not be that hard. So let's take a look what we're doing here. So before we call into this function, this is the main function. The C library function will call the main function, right? So the very first instruction of the main function, the ndbr, ignore that. Then the second instruction is node effective address ESP -4 to ECX. So let's say before we start, ESP will point to the return address, which is somewhere in the C library function that calls the main function. So that's a return address. ESP points to that. So after this instruction, ECX will point to 4 bytes higher than that. Okay. Now after that, we will have a logic AND instruction, ESP with 7 Fs and 0. So what does this instruction do? What is the logical AND from 1 to 1? 1 logic AND 1 will get 1. 1 logic AND with 0 will get 0, right? So basically, what this instruction does is to clear the last 4 bits of ESP. Doesn't matter what the ESP value is, it's going to get smaller. Well, unless the ESP, the last 4 bits is already 0. If they're not 0, it will be changed to 0 because this is AND. So you see what this is doing? This is trying to move ESP to a lower location, which is has some kind of a 16 bytes alignment. That's the purpose, right? No matter original where the ESP is, the ESP originally could be points to some place under with 2, under with 4, but now we're going to change it with 0. So we're going to move down, and so we have a new ESP. The problem is this: the ESP will not point to the return address anymore. Eventually, we still wanted to return to the return address. That's why we have a lot of push here to push ECX -4, the value at ECX -4, which is the return address, to the stack. So now ESP will point to the return address again, but we may have some garbage in the here, which doesn't really count. Okay, doesn't really matter. So then after that, we have the new setup of the like the original, like the regular functions, push EBP, move ESP, BBP. So basically, the whole thing is we have two copies of return address on the stack. At this point, we don't even know which one will be used. Well, most likely this one. Otherwise, why do they have that? And we have some garbage here. We don't know the size. We only know the size at runtime. Okay. So everything after that seems like regular, except that there is another push. Push ECX points to the original argc here. Then at the end of the function, we will have so at the end of the function, let's say, where are we? We're going to leave. After leave, ESP will point to the old our return address. Then eventually we got return. So if you debug the whole thing, you realize that if you are starting from buffer, you're trying to override that 24 bytes something, override this return. This return is not the return actually used by the main function. The actual return used by the function is actually the original return, which is at some higher address. Okay, that's what happens here. So to craft this exploit, you need to carefully design your your exploit, so it will be copied around. Eventually, you can figure out how it works. Okay, so if you want to figure out how this works, debug by yourself and also look at my slides. Do that instruction by instruction. Eventually, you can get it. Okay, we're not going to debug this program in class, well, something like this will not show up in the exam, and that's what I promised you. Okay, so let's go back to what we are really want to talk about today. So far, we have been learning several different methods to do buffer overflow to change. Eventually, our goal is to change the EIP. No matter we directly change the return value, return address on the stack, or we change the EBP on the stack, the goal eventually is to take control of the EIP to let it point to our share code. So if we look at what conditions we depend on to pull off all those attacks, we can summarize at least those 4 conditions. The first one is we need the ability to put the share code onto a stack. Either inject that in a buffer, put that in the environment variable, or command line arguments. But those are on stack. That's so far what we're doing. We're injecting code onto the stack. So second half of the class, we will do something. We do not need to inject any class, any code onto the stack. We will reuse whatever is on the address space. Today, even we will do one of that, but it's a very specific case, not a generic case. The second part is the stack is actually executable, which doesn't make sense because who will ever, if you are a compiler designer, you are a program developer, why would you ever let the stack executable anyway? That's supposed to have some data there, just data, not code, right? So that's the second condition so far we rely on. Also, we need the ability to overwrite the return address on stack before the corresponding return instruction. Also, we need to know the address of destination function. Sometimes not necessarily the accurate address, we can just guess. So as a defender, how do you defeat this attack? You take out those conditions one by one. You think about how can I take out one condition, so at least I can defeat the current attack. Maybe the attacker can find another smart way to bypass that. Then you take out another condition. So that is usually what happens in security research. It's an arms race between attacker and defender. Attacker finds some new approach, and defender come up with a new solution. Then the attacker find out a new way to bypass that defensive solution. So it's a never-ending game like this. And sometimes you will find something no one thought about before. It's a breakthrough. It could be either at the attack side or the defense side. So today, first we look at the first defense, which is how about we just make the stack not executable. It's not supposed to be executable in the first place. Okay, so this is a defense called data execution prevention, DEP. On different architectures, you have different names. This is currently already supported by all the CPUs. That's why I mentioned different architecture. Different names, DEP, WX, or execute. Well, so this means this is a memory region. This memory region is either writable or executable. If you want to make this memory region writable, then we are not going to execute anything here. For example, the stack is writable. The attacker will be able to write code there, share code there, but we will never execute from there. If we execute there, the CPU will generate a fault, or just the NX feature on some CPUs. So actually, the idea here, the fundamental idea is to split code and data. Code should be in their own region, which is executable, and data should be in their own region, which is never should be executable. So this idea is not new. This idea is from the very beginning of any computer design. So most of the computer systems we use right now, we use an architecture called this von Neumann architecture. So in this architecture, this is architecture our laptop, our desktop, or our powerful computers use. So basically the same memory and bus can be used to store both data and instructions. So the problem of this is sometimes you can misinterpret data as instructions. The advantage of these architectures is the control unit retrieves data and instructions in the same manner from the memory. So the design and the development is simplified. It's cheaper and also faster. So we can see one of the disadvantages here is actually security. Data can be treated as code, which they should not be. So also those architectures, they do not only apply to our main memory, they can be applied to any memory in our computer system, from the cache to main memory, even to secondary memory. The other architecture is called the Harvard architecture, in which the data and code are stored in separate memory units. Right now we do not see many computers using this architecture, but in real world, some of the microcontrollers, so very low-end IoT devices, their CPUs like Cortex-M, 4, Cortex-M3, maybe I'm not sure about 4, maybe 3 is. So those very low-end devices, like their CPUs are not called microprocessors. The computers you use, we use microprocessors. The CPUs they use, we call microcontrollers. They're still CPUs, but much low end. We're talking about $1 per CPU or even cheaper than that. But the laptop you are using $200 a piece of Intel CPU. We're talking about very cheap CPUs. And those CPUs, a lot of them actually are using the Harvard architecture. So on those von Neumann architectures, how do we want to end the support to separate code and data using that data prevention execution technique? So some old computer systems, for example, in 2020s, those Intel CPUs, the read permission basically implies executable. There is no separate permission for read and executable. So if a memory page is readable, it is also executable, which means if its memory page is readable and writable, it is also writable and executable. In 2003, AMD first introduced NX, no execute bit for pages. So this is obviously in MMU. So for that, the operating system can set this memory page is not executable. So this is obviously a hardware feature. Part of MMU operating systems rely on that. So the Windows, they started supporting this feature because it starts from the hardware. Then the operating system need to utilize this feature. Windows started using this feature in 2004. Linux also started this in 2004. So it has been almost 20 years. That's why now all your computing devices have this feature. And by default, not only the stack is not executable, or also the heap is not executable. So the modern computers, they basically separate the read and execute permission with different hardware changes. Okay. So then why so far all the programs we have been using, we can't put the shellcode on the stack? That's because when I compiled the programs, I gave GCC this specific option to ask GCC to disable this protection, which means if you compile a program with GCC without giving it any option, your program is protected. The stack is not executable. However, when I compare so far the programs we have been using, we are using this option. So let me show you how we compile all the programs by so this is a make file for overflow return 4. Overflow return 4 have been you already hacked this, but there will be many different versions of this program you're going to hack, and each version there will be some new protections, make it even harder to hack. For example, the one you have been using so far is this overflow level 4, and you can see first one, this is a flag telling the stack is executable. This is a flag telling the stack is executable. And also we have another flag telling we're not going to use another default security feature called the stack protector. This is also called the stack cookies or stack canaries. Probably we'll talk about next class. For the version we're going to hack today, we're not going to have this flag. So the stack is not executable anymore. However, we still do not have stack cookies to protect us. Okay. So later you are going to hack another version. You can see we're not giving it any options. So this is the default option right now you use to compile any program. It adds several layers of at least 2 layers of protection there. Okay. So if you compare those 2 programs, let's say, let's do this on the server. On the server, you can see we have this version, overflow return 4, low exe, and also no, this one is no canary. The TA gave it a weird name here. Anyway, let's say if we do a read elf, I hope you still remember this command. Then we do this program. You can find the segments or sections of this program. And here you can see this is a stack of this program. And the stem of this program is not executable, right? It's writable, but there's no E here, not executable. Also, you may find other sections. For example, the code section obviously is executable. So if, remember, this is the one we're going to hack today. So if we go back to the version we hacked last week, overflow return 4, this one. We do the same read elf. We do the same read elf. What's going on with this one? Is this one? No, not this version. Should be. Oh, should be this version. Overflow return 32, this version. So if we look at this version, you can see the stack here has an E here, means it is executable. That's why we can put the share code there and execute that. Share code on the stack. So obviously, this approach only stops you from executing code from the stack. It's not perfect. Remember, we have overflow local version 1 and 2. So you are overflowing a local variable. Remember that? So this approach cannot stop that because you're not injecting any code there. You're only overwriting a local variable. So you can still overwrite. And also this approach doesn't really stop you overwrite the return address or the saved EBP on the stack. You can still overwrite that. You just cannot overwrite that and make it point to somewhere onto the stack, right? So because of this, there are many ways we can bypass this defense. So the first way to bypass this defense is a technique called the return to libc. So previously, we can call our approach is return to our own share code. So next, we're not going to return to our own share code. Our own share code is injected on the stack. We're going to return to some existing code, which is already in the address space of the program, and it's executable. So the idea of return to libc, actually you have been familiar with. We just haven't called it return to libc yet. Remember, you have been overwriting the return address to call the print secret function. The print secret function is not a libc. It's our function, right? We developed that as part of the program. So the only difference between return to that and return to libc is you are not going to return to any function that is in the program itself. Instead, it's in the C library. But the C library is always loaded in the program's address space. So you can call those functions. You can return to those functions, right? So the technique is exactly the same. And you already know how to do that in 32-bit version. You can set up the as many register or many arguments as you want, which means you can call any function, but you probably can only call one function. Okay. So this approach is first discovered by some guy, a pseudonym called Solo Designer, back in 1997. So remember, the first buffer overflow was back in 80s. Then the slash the stack for fun and profit, that white paper was kind of like in 94. And 3 years after that, someone discovered the return to libc. Okay. So this one was actually discovered before DEP was deployed. DEP was deployed in 2004. So even though we know DEP is not perfect, the vendors still added that support to the CPU. So the reason we want to return to libc is we want to bypass that non-executable stack. We're not going to inject anything to the stack. We just want to call into a C library function and make it do anything we want. One of the very useful function is the system function. This is not a system call. This is a library function. Okay. This is C library function. For example, on our server, you do man system. It tells you how to use this function. This function, you basically give it a command, and it will execute that command. That's it. But you can see the manual section for this entry is level 3. Is what is this called? segment 3 or whatever. So 3 here means this is not a system call. 2 means 1 is a command line, is a command. 2 is a system call. 3 is just a function. Okay. For example, if we do let's say open. Open, if we do main open, it shows 2, which means even though it looks like a say function, but underlying this is a system call. But the system one, it's not. This is just a function. Underlying is not a system call. Underlying basically is creating a new process. So the system call should be exe cve, something like that, right? So this function actually eventually calls the system call exe cve, something like this. So it basically translates a string, a name of string, to call this function, to call the system call to do this. Any question here? Do anyone understand the difference between system call and the function call here? Okay, so system is basically a C library function. So our goal here is just to we have 2 goals. The first goal is to give us a shell. The second goal is maybe you just print out the flag, right? So how can we do that? We can either do this system bin sh, just give bin sh or any other shell you want or any other program you want, and use that as a string, as an argument. Then you return into this system library function. Then this bin SSH will be executed as a new process. So it can give us a shell. Or we can, here we can do a cat flag. Then the system will directly create, you will try to execute the command, the cat flag for us. Well, the problem is on our server, this is the same problem we have here, but before, the system will create a new process. So the new process will not inherit the root privilege. So on our server, we can do return to libc, but you will not be able to get the flag because no matter you do cat or you do get a shell, that thing will not have the root privilege. So you still do not get the flag. But on some old servers, this attack still works. Okay. So today we are still going to do this attack. We're going to get a shell. We're going to execute the cat thing, but it will not going to really work to give us the flag. Okay. Anyway, what's going on here? Close this. Okay. So the program we are going to crack today is still overflow return 4. But this one, there's no, the stack is executable and there is no canary here. I'm not sure why the TA gave it a weird name here, but that's basically what it means. Okay. So let me remind you the program, the vulnerable program. We have a main function. Main function has a vulnerable function vulfoo. Then it calls the print IP the full. If the vulnerable function has a buffer here, which is 30 bytes, then there is gets. So gets will take input from std. So our goal is to, we cannot inject the shellcode. Our goal is to return to the C library function system, get a shell, and also get try to catch the flag for us. So let's see how are we going to approach this. I'm not sure which challenge I mean, so I'm going to do this. Here. So in your homework later, you can try to use the exploit you used before on this one. So the same exploit you used for return to overflow return 4. You can see if it works. It should not work. Okay. Because it's the exactly same program. The only difference you can say is the options I gave when I compile this. So to do this, what is the first step? we need to know the address of that return the system function, right? The same as we find out the address for the print secret function, right? So there are many ways to do that. We just use either way. We just do a GDB, then we run this program. We set a breakpoint at the beginning. We run this program. Then we just do a print system. Okay, we just do a p system, and it gives us the C library function system's address. This is its address. Okay, now we have this function's address. What's the next thing we need? What is the argument for this one? What? Yeah, so what is BSH? It's a string, right? Okay, so how do we get that string? Okay, we can put it in the buffer, okay? We can also put it in command line arguments or environment variable. Anyway, it's just a string, it's not code, right? So also, we don't have to do that because the string being sh is already in the C library. The C library has that, okay? For example, let's find out what library we are using here. C library we are using here. We use LDD on this program, and the LDD tells us what library, dynamic libraries this program uses and where it is loaded. Since we disable the address space layout randomization, it always give us the same address. Okay, so after midterm, we're going to enable address space layout randomization, so things get a little bit more difficult. Okay, so this is a C library we are using. You see, this is obviously what is it called? Symbol link. This is actually the library file we are using. Is this file? So this file actually already have that. Let's do a cat this. So we just grab bin. Oh, we should not do cat. We should do strings. Sorry. So strings will give all the readable strings in those binary. So we do a strings, then we do a grab bin. We can see that there are a lot of text in those C library function, C library file already. And one of them is being sh, okay? It's already there. So this string is already in our program's address space. We just need to find out where it is. So to do that, we go back to GDB. There is another command I want to show you guys. It's basically, you can use the find command to search in the address space of the program. If you don't know how to do that, you can do find, help find or find help. Find this. Yeah, you can do help find, then it tells you how to use this command. Okay. There is another command I want to show you. It's called info. Info files tells you all the segments of this file. As you can see here, I do an info files. GDB tells me where every section in the program is loaded in the address space. So you can see those 5, 6 addresses. Obviously, those are part of the program itself, not the C library. If you keep going down, you can see those things are C libraries or Linux libraries, other loaders libraries, right? And I'm telling you here, the string is actually in the C library. And because it is a string, it is actually in the C library read-only data section. Let's try to find that read-only data section. Oh, here. See? Because we're looking for a string. That's a read-only data, no one is going to change that. So this read-only data section of this C library is actually in this place. So we can just search this address space to find that string. We do a find those two, the beginning and end. And what we are trying to find is just the string application. We can verify that by using exam memory, right? With exam, we know that's a string. So put this address there to verify if that's what we want. Yeah, it is what we want. Probably near zero there are more strings. So let's do maybe we print out 5 strings there. You can see, well, there are other strings as well. But we just don't need them. There may be many strings there. Okay, we don't need them. So the only one we need is this. So now we know the where we want to return to. We know where the we need to write down this address. Write down here. This is the strings address. Where is the system address? System address is here. So those are the 2 addresses we need. Now we just get out of the GDB. We want to buffer overflow this program. I don't remember how much we need to buffer overflow this, so let's do our object dump to figure out. So we're looking for the vol foo. Okay. So vol foo here is EBP. The buffer is at EBP minus 30, which is 48 bytes. The 4 bytes of garbage for saved EBP. So totally we need 52 bytes of garbage, right? So, okay. So how we construct this exploit? It takes from string, it takes from command line, or it use, where is it? Oh, it use gets. So it takes from std in, right? Okay, so from std in, so we just do we do a Python 2. Say print. We need 52 bytes of garbage first, right? 52 bytes. Then we need the address of. So here is basically the return address, and we need the address of the system function, right? So the system function is this one. So that's what we want, which is 3058 E1 F7. Okay. After that, another 4 bytes of garbage. Okay. If you do not remember why do we need that 4 bytes of garbage, go back to our my videos maybe 2 weeks back. So I showed you why we need another 4 bytes of garbage here. So anyway, we need another 4 bytes of garbage. So after that, we will have the strings address. Five to 23 F6 F6 F7, right? That's a string. Okay. So after we print out this, we should get a cat there. Then we pipe this into the program. Oh, okay, looks like it works. We're supposed to get a share now. Let's see if we get a share. Yeah, we get a share. Okay. We didn't inject any share code into address space. We just reused something in the already space. So this is not the code injection attack anymore. This code is a code reuse attack. So there is a more advanced code reuse attack called a return-oriented attack, which we started the second half. That one is amazing. You will be surprised by that one. Most people, when the first time they say that one, they're surprised. They're surprised. Okay. The problem of this one is obviously we don't have permission. We are still CTF. Okay. We don't have the permission to cat the flags. Let's say we cat flag. We don't have the permission. Okay. But on some of the servers it works. Some older servers it works. Just on our server, it doesn't work. Okay, but we can, let's say we want to change this a little bit. We want to, instead of executing, create a new process for the shell, how about we just execute can't permission? So how do we do that? We don't have the string. Obviously, we cannot find the string can't flag in any library, right? That makes sense. They have that. Let's say they have we do a can't. We find all the can't. You can see there are a lot of string with can't, but there's no way we're going to. There's a can't flag, right? So what we can do is obviously we can do we can put this in environment variable. Let's say just to say then what is our string here? Python 2. Let's do this. Print cat flag, right? This should work. But what if here? Well, the problem of this is we still want to get the exact location of that string, cat flag. In our shellcode, we're trying to put a huge slat here. So here, how do we put a slat? What is a slat here? What is a not slat? Equivalent the same here. What? Exactly. Who said that? Can you say that? Yeah, the white space, right? It's the same as, for example, let me just type this on. So you can do can't flag here. We don't have permission, but you can add a lot of white space here. It's basically the same thing, right? So, but it's kind of work like a stat for us, right? That's why we can add a huge stat here, just a white space. Then we get 500 bytes of stat. We add this one. We export this. Then let's see if we have that set. Okay, it is set. Okay, this is our command. Okay, but this command is not code. Still not code. It's just a string. Okay. Then we can get the relatively accurate address of this thing. So this is kind of the address. So we can do this by the same exploit, the same system address. We can change that. We only need to change the command. The command now we have is at this address. So we change that. So that's 26. Since we have a big slat there, then we just do maybe 88 dd ff. Okay, this one we don't need a can't anymore. So we press the same. See? That one get executed. Just the permission below, but it worked. But after that, we get segment 4, but doesn't matter anymore. Okay. So on some servers, use this approach, we can also get the flag. Cool. So that is basically how return to libc works. So let's say, so far, we have been discussing two different types of tags. One is overwriting, one is by injecting shellcode there, another one is not injecting shellcode. But all of them, the common thing of those two attacks is we are all hijacking the control flow. Okay, at some point we hijack the control flow. So all of them can be called the control flow hijacking attacks. And this kind of attack exploits a program error. It's usually a memory corruption error. to subvert the intended control flow of the program. And to do that, we usually need to overwrite a code pointer somewhere in the memory. There are many code pointers in the memory. So far, we have been saying the return address, that's a code pointer. But in C programming, there are function pointers. And so function pointers, usually global variable or local variable, they are also code pointers. And even more code pointers in C++ programs, because each class, at the beginning of each class, there's a virtual table for C++ objects. And the virtual table has a lot of function pointers. So all of them are supposed to point to a function. So they point to some code. So as long as we can overwrite one of those and somehow call that, we gain the control of the EIP. So two attacks you are already familiar with: code injection attack, which you inject share-code. Another one is code reuse attack, which you do not inject the code, but you subvert the intended control flow to invoke unintended execution paths inside the original code. So far, just now I showed you how to do return to libc. Second half of the class, we're going to do a very advanced one. It's called return-oriented programming. Let me explain you a little bit what's the difference. In return to libc, what we're doing is we return to the middle, or we're return to the beginning of a C library function, right? But we don't have to return to the middle or the beginning of any function. In the previous example, the print secret one, you have been doing that. You are returning to the middle of our print secret function, which calls the print flag function, remember, right? But still, you are returning to some place that's supposed to be valid instructions. But you already see that the instructions in our architecture x86. Let's do a object dump of anything. obj dump. Look at any function here. So the instructions, they have different lengths. Some of them are very long, like this one, 4 bytes, this one, 5 bytes, this one, even 6 bytes. Some of the instructions are short. This one is 1 byte, this one is 2 bytes. The problem of this is any byte can be the beginning of an valid instruction. So far, let's say we've been jumping to over here, right? The beginning of a function, or we have been jumping to the beginning of a valid instruction. What if we jump to the middle of an instruction? The middle of for example, here we have an AND. Let's say we do not jump to here 80, we jump to here, C3 or 9F. What will the CPU do? Most likely, it will not be a valid instruction. So the CPU will generate an error. But if we carefully search that, there will be a lot of valid instructions. And we can even kind of like weave them together to do something interesting. For example, this one, C3 is actually the return. So see here, this is the return instruction. Return instruction, the machine code is C3. You can see this part, there's a part of it is C3. What does that mean? If we jump to here, the CPU will think we're running the instruction return instead, not the AND, right? So that's the idea of return-oriented instruction. We're going to check every byte, use that at the beginning to try to disassemble this to see what kind of useful instruction we can find. Then we can find a lot of useful instructions. They're not supposed to be instructions in the first place, but they are there. Okay. Then we carefully collect them together. Then we can do arbitrary things, like we can execute, we can create a shell. Okay, so that is what we're going to do at the second half of the class. Okay, go back here. Also, there is another related attack called jump-oriented programming, quite similar as return-oriented programming, but it doesn't end with a return instruction, it ends with a jump instruction. Similar things. Okay, we still have like 20 minutes. So in this 20 minutes, I will give you another challenge. It's also on over the wire. It's the maze level 2. You already did the behemoth level 2. Same structure. You are using those credentials to log in and try to hack that and get the password to maze 3. Okay, so I will not tell you what the vulnerability is. You need to figure out this by yourself, what the vulnerability is. It is not necessarily the vulnerability types we talked so far. It could be easier than that. It could be a little bit harder than that. Okay, you can get started. to configure all the errors, all the internet code. Just debug some arguments, to say all those arguments moves in this program and where the program is.
Okay, our post homework soon. See you guys next week, and also let me see. So next week will be our last week before the midterm. So we're going to have the midterm March 14th.
The week of March 14th, both classes will be midterm. So there will be several severe challenges.
But after that, we have the spring recess for a whole week. When we come back, we study under vulnerabilities. Cool.
See you guys next week.